Okay, so this is going to be the second half of the determining reaction rates lecture. We didn't quite finish yesterday during class, so I need to spend a little bit of time with it now so that we can kind of finish and you guys can have some homework this weekend, which is I know exactly what you want. So we need to talk about half-lives a little bit, and this is something that does come up on the AP exam on occasion. So half-life is defined as the time needed for the initial reaction concentration to drop by half of the starting value. So think of it in terms of like, if I have 100 grams, how long does it take to get to 50 grams? And then how long does it take to get to 25 grams, so on and so forth. And that's the half-life. We can figure that out by using the integrated rate law, usually because it's a first order reaction. We'll talk about that in a second. But we're going to do a couple of examples and then be done with the day. So there are first order, second order, and zero order half-lives. In the first order half-life, the half-life is independent of the reactant concentration, and this is the formula that you will use if it's a first order reaction. The natural log of 2 is 0.693, and I believe even on the AP exam, they just give you this. T1/2 equals 0.693 over the rate law constant. So I don't even think you need to really know this. You just have to know that that's for a first order reaction. The second order reaction takes the inverse of K and the initial concentration, and that's inversely proportional. And a zero order takes the concentration divide over the inverse of 2K. Again, we don't see a lot of these, so the first order ones are the ones that we're going to focus on today. Okay, so a plot of N2O5 versus time for 3 different half-lives. So this is kind of what it would look like. We would start, and every half-life, which is the same, which appears to be 24 minutes, 24 minutes, 24 minutes, the number of spheres decreases by half. And that's all this is trying to show you. So if we start at a concentration of 0.6, when we get to the concentration of 0.3, we'll get to a concentration of 0.015, and we'll get to a concentration of whatever 7.5 or that whatever that is here. So after each half-life, the concentration of the spheres is what we're looking at. And so the first example that we're going to go through is we're using a first order reaction that has a half-life of 20 minutes. And the first thing we're asked to do is calculate the rate constant for this reaction. So we're going to use the formula T1/2 equals 0.693 over the rate constant. So because we know the half-life is 20 minutes, I'm going to take that and substitute that here and say I have 20 minutes is equal to 0.693 over K. And when I solve for K, I get a value of 0.0347 per minute. So that's my rate constant. I can go ahead then and plug that into the integrated rate law for a first order reaction and calculate the final concentration or the initial concentration or anything along those lines. So that's how we use the half-life formula. And for B, the question is asking us how much time is required for this reaction to be 75% complete. And so I guess think about it again in terms of if I have 100 grams and I cut that in half, that would be 50 grams, and I cut that in half, that would be 25 grams. And so if the idea is to go to 0, we're looking at, so we're looking at 20 minutes, that's 50% done. 25 minutes would be 75% done. So this is really a mathematical deduction, or not a mathematical, this is a logical thinking problem, in which case it's going to go from 100% or 100% to 50%, and from 50% to 25%. That means that we've used up 75% of the reactant, so that's going to take us for 2 half-lives, so that will be 40 minutes. And I hope that makes some sense. The next thing we have to talk about is nucleotides. And nucleotide decay has to do, since we're talking about radioactive decay, it depends on the actual nucleid itself. All decay reactions are first order reactions. And the only difference is that we consider the number of nuclei rather than the concentration. And there's this formula that's associated with that. And again, the half-life for this, because it's a first order reaction, is going to be T half is equal to 0.693 over K. Nuclear decay problems can also be solved using first order integrated rate law, which I'm going to show you how to use in the next problem here. Again, this doesn't show up very often. We just want to work our way through it and use logic to do that, so I'm going to show you how that works. So at this point, I'm going to solve for the, or I'm going to simplify the natural log of 1.5, which is 0.405 milligrams equals negative 0.0248 per days, plus the simplification of the natural log, which is 1.75 milligrams. Bring 1.75 milligrams to the other side, and I get negative 1.35 milligrams equals, it should be times T plus. So that's going to be negative 0.0248 per days. And when I solve for T, I'm going to get a value of 54.4 days. So what this tells me is that it's going to take 54.5 days almost to take 5.75 milligrams of chromium-51 to decay to 1.5 milligrams. And so that's that, and this is your homework for the weekend. So go ahead and enjoy that, and I will see you guys on Monday.